In electrical systems, the most important design criterion is, and must always be, the protection of people from electric shock. At the end of the day, equipment can be replaced. Systems can be repaired. But human life? It cannot. That is why protection against electric shock is not optional. The principle behind protection against electric shock is actually very simple. It is based on two rules. Rule 1. Hazardous parts should not be accessible. Rule 2. Accessible parts should not be hazardous. If both of these conditions are satisfied, the risk of electric shock is drastically reduced. Before we see how these rules are applied in design, we must first understand why electric shock is so dangerous. When electric current flows through the human body, it interferes with the normal functioning of vital organs. This leads to four main physiological effects. First, muscular tetanization. Muscles contract involuntarily, and the victim may not be able to let go of a live conductor. Second, breathing arrest. If current passes through the muscles that control breathing, normal respiration is disrupted. This can lead to suffocation or severe injury due to lack of oxygen. Third, ventricular fibrillation. The most dangerous effect. Electric current disturbs the normal rhythm of the heart. Once triggered, this condition may continue, even after the current has stopped. Fourth, burns. Caused by heating due to the Joule effect from the current passing through the human body. Among all these effects, ventricular fibrillation and breathing arrest are the most dangerous. They can be fatal. Whether an electric shock is harmless or fatal depends on three key factors: the magnitude of the current, the path it takes through the body, and how long the current flows. To help engineers design safer electrical systems, IEC Standard 60479, Part 1 classifies the effects of alternating current on the human body into 4 zones, based on current magnitude and duration. Zone 1 represents currents so small that they are not even felt. No reaction occurs, and no harmful physiological effects are expected. As current increases into Zone 2, it becomes perceptible. Muscle contraction may occur, but harmful effects are still unlikely. In Zone 3, the risk becomes critical. Strong muscular contraction, difficulty in breathing, and reversible disturbances of heart rhythm may occur. Zone 4 is the most dangerous zone. Here, ventricular fibrillation, cardiac arrest, breathing arrest, severe burns, and a high probability of death are possible. With this understanding, let's return to the two simple rules we started with and see how they are applied in electrical system design. Together, these two rules address electric shock dangers, which appear mainly in two situations. The first situation occurs when a person touches a part that is live during normal operation. This is known as direct contact. Because this danger exists even when everything is working normally, the protection against it must always be present. The protection against direct contact is also called basic protection. Why basic? Because it works before anything goes wrong. Basic protection exists to enforce the first rule. Hazardous parts should not be accessible. This is achieved by simple but powerful measures, such as protection by insulation of live parts. For example, cable or busbar insulation, where live conductors are completely covered and cannot be touched. Protection by means of barriers or enclosures, such as switchgear panels or motor terminal boxes, which prevent direct access to live parts. Protection by placing live parts out of reach. For example, overhead conductors installed at sufficient height so they cannot be accidentally touched. Or protection by the use of obstacles placed between the live parts and the operator, which prevent unintentional contact. As long as these measures remain intact, direct contact, and the danger it brings, is prevented. But electrical systems do not remain perfect forever. Insulation can fail. Internal faults can occur. When that happens, parts that are normally safe to touch, such as switchgear panel enclosures or motor frames, can unintentionally become live. This creates the second situation of danger, known as indirect contact. Protection against indirect contact is also called fault protection. Why fault protection? Yes, because it assumes that something has already failed. And its purpose is to ensure that accessible parts do not remain hazardous after a fault. At this point, the first rule is no longer enough. Now, the focus shifts to the second rule. Accessible parts should not be hazardous. In low-voltage systems, protection against indirect contact is achieved through three coordinated measures: earthing of exposed conductive parts, equipotential bonding, and automatic disconnection of supply. Earthing provides a low-impedance path for fault current. Bonding ensures that simultaneously accessible metal parts remain at the same potential. An automatic disconnection of supply, within a specified time, ensures that dangerous touch voltage does not persist long enough to cause harmful physiological effects. In low-voltage installations, protection against electric shock must follow national regulations and relevant international standards. Before we close, one important point to remember. Protection against indirect contact, or fault protection, in medium and high-voltage systems follows a different design philosophy and is covered by dedicated standards. Thanks for watching.